So here's something worth thinking about tonight. Right now, wherever you are surrounded by elements. And I don't mean that in some vague, poetic way. I mean it literally. The oxygen you're breathing, that's element number 8. The carbon in every cell of your body, that's number 6. The iron carrying oxygen through your blood right now, that's 26. The calcium in your bones, 20. The nitrogen in the air around you, 7. The copper in the wires running through your walls, 29. The silicon in the glass of your window, 14. Every single thing you can see, touch, smell, or taste is made from the same basic set of ingredients, and there are only about 90 of them that occur naturally. 90 building blocks. That's it. That's what the entire visible universe is made of. Every mountain, every ocean, every star, every grain of sand, every blade of grass, every living thing that has ever existed, all of it built from fewer ingredients than you'd find in a well-stocked spice cabinet. And we have a map of those ingredients, a chart, a single, elegant, surprisingly beautiful document that organizes every known element in the universe into a pattern so deep and so reliable that it can predict the behavior of substances nobody has ever seen. It's called the periodic table, and it's hanging on the wall of every chemistry classroom in the world, and most people glance at it and see a grid of letters and numbers that feels about as exciting as a tax form. But here's what they're missing. The periodic table is one of the greatest intellectual achievements in human history. It's a story of obsession, rivalry, brilliant guesses, spectacular failures, and at least one dream that changed everything. The people who built it were not dull. They were alchemists and revolutionaries, dreamers and meticulous weirdos, and more than a few of them died for their work, some on the battlefield, some in the laboratory, and one on the guillotine. So settle in, get comfortable. We're going to walk through the whole story tonight, how humanity figured out what everything is made of, one element at a time. We'll start in the ancient world, where the question first took shape, and we'll end up in particle accelerators, where scientists are creating atoms that have never existed in the history of the universe. And if you drift off somewhere along the way, that's perfectly fine. The elements will still be here in the morning. They've been here for billions of years. They're in no hurry. Let's go back to the very beginning. And I mean the very beginning. Because the first people to seriously think about what stuff is made of, what the fundamental ingredients of reality are, were the ancient Greeks, around the 5th and 6th centuries BCE. And the answer they came up with was elegant, intuitive, and completely wrong. You probably remember this from school. The Greek philosophers, particularly Empedocles around 450 BCE, proposed that everything in the world was made from 4 basic elements: earth, water, air, and fire. Mix them in different proportions and you get different substances. More earth makes things solid and heavy. More water makes them fluid. More fire makes them hot and changeable. Aristotle picked this up and ran with it, adding a 5th element, ether, the stuff the heavens were made of. And this 4-element model became the dominant framework for understanding matter in the Western world for nearly 2,000 years. Now, the thing is, it wasn't a terrible idea given what they had to work with. Think about it. If you heat water, it turns into steam, so maybe water is becoming air. If you burn wood, it produces flame and leaves ash behind, so maybe wood is a mixture of fire and earth. There was an internal logic to it. The problem was that it wasn't testable in any rigorous way, and it didn't actually predict anything useful. You couldn't use it to make new substances or explain why some things dissolved in acid and others didn't. It was a philosophical framework, not a scientific one, but it held on because, well, nobody had a better idea. And because Aristotle said it, and for a long time in European intellectual history, that was pretty much the end of the conversation. But alongside this philosophical tradition, there was another tradition running in parallel. A stranger, more secretive, more ambitious one: alchemy. And here's where things get fascinating, because alchemy is usually dismissed as a bunch of charlatans trying to turn lead into gold. And while there was certainly plenty of that, the reality is much more interesting. Alchemists were, in many ways, the first experimental chemists. They built furnaces, distilled liquids, mixed acids, heated metals, cataloged reactions. They developed techniques that real chemistry would later inherit: distillation, crystallization, the use of chemical solvents. What they lacked wasn't ambition or skill. What they lacked was a correct theory of what matter actually is. The central obsession of alchemy was transmutation, the idea that one substance could be transformed into another if you found the right process, the right catalyst, the right mystical ingredient. And the ultimate goal for many alchemists was chrysopoeia, the transformation of base metals like lead into gold. They believed this was possible because they believed, following the Greek model, that all metals were fundamentally the same stuff, just in different proportions. If lead and gold were both made from the same basic elements, then surely you could rearrange those elements. You just needed the philosopher's stone, a legendary substance that would catalyze the transformation. Now, here's the delicious irony. Transmutation is real. You actually can turn lead into gold. We've done it. Modern nuclear physics has achieved exactly what the alchemists dreamed of. But you need a particle accelerator, not a philosopher's stone, and the energy cost is so enormous that the gold you produce is worth far less than the process costs. So the alchemists were right about the possibility and wrong about everything else. But their centuries of experimentation, their cataloging of substances, their development of laboratory techniques, all of that laid essential groundwork for what came next. And what came next was a revolution. It started in 1661 with a book by an Irish-born natural philosopher named Robert Boyle. The book was called The Sceptical Chymist, and it was, in a very real sense, the birth certificate of modern chemistry. Boyle did something deceptively simple, but profoundly important. He challenged the entire idea of four elements. He said, "Look, you keep telling me everything is made of earth, water, air, and fire, but can you actually show me that? Can you break a substance down into those four components and then reassemble it? No? Then maybe those aren't the real elements. Maybe we need a completely different definition." Boyle proposed that an element should be defined as a substance that cannot be broken down into anything simpler by any chemical means. If you can't decompose it further, it's fundamental. It's an element. That sounds obvious now, but in 1661, it was radical. It shifted the whole conversation from philosophy to experiment. Stop theorizing about what elements should be. Start testing what elements actually are. Take a substance, try to break it apart, and if you can't, then you've found an element. Now, Boyle himself didn't identify many elements. The techniques available in the 17th century were limited, but he opened the door. He gave future chemists a method, a criterion, a way of thinking that would eventually lead to the periodic table. And between Boyle and that table, about 200 years of painstaking, messy, sometimes dangerous chemistry had to happen. Scientists had to actually identify the elements, one by one, separate them, characterize them, figure out what made each one unique. And nobody did more to push that project forward than a man who came along about 120 years after Boyle, a French aristocrat, a tax collector, and the greatest chemist of the 18th century. His name was Antoine Laurent Lavoisier. and his story is one of the most dramatic in all of science. Lavoisier was born in Paris in 1743 into a wealthy family. He studied law, as his father wished, but his real passion was science, chemistry and geology in particular. He was methodical, precise, almost obsessively quantitative. In an era when most chemists were still working with vague descriptions and approximate measurements, Lavoisier weighed everything. He built custom balances accurate to fractions of a grain. He insisted that every experiment be quantified, that every input and output be measured, that nothing be assumed. And this rigor led him to what might be the single most important discovery in the history of chemistry. Here's the thing that chemists in the 1770s couldn't explain. When you burn something, wood, candle wax, phosphorus, anything, what's actually happening? The prevailing theory was something called phlogiston. The idea was that flammable materials contain a substance called phlogiston, and when they burn, the phlogiston escapes into the air. It was a theory proposed by the German chemist Georg Ernst Stahl around 1703, and it was widely accepted. When metal rusts, it's losing phlogiston. When wood burns, the phlogiston flows out as flame. But Lavoisier noticed something that didn't fit. When you burn phosphorus, the product, the ash, the residue, weighs more than the phosphorus you started with. That's the opposite of what phlogiston theory predicts. If burning means losing phlogiston, the product should be lighter. Instead, it's heavier. Something is being added, not removed. Lavoisier realized that burning isn't about losing some mysterious substance. It's about combining with a very real substance from the air. He isolated this substance, characterized it, and named it oxygen, from the Greek words for acid former, because he thought, incorrectly as it turned out, that oxygen was a component of all acids. This was a revolution. Lavoisier dismantled the phlogiston theory, replacing it with the oxygen theory of combustion. He showed that air itself is a mixture, primarily of oxygen and what he called azote, nitrogen, and he established the law of conservation of mass. In a chemical reaction, matter is neither created nor destroyed, only rearranged. That principle is so fundamental that everything in chemistry depends on it. Every equation you've ever seen balanced, with the same number of atoms on each side, that's Lavoisier's law. And then Lavoisier did something else that's directly relevant to our story. In 1789, the same year the French Revolution began, he published his great work, Traité élémentaire de chimie, Elements of Chemistry. And in it, he included a list of what he believed to be the true chemical elements, 33 of them, substances that could not be broken down any further. Some of them were correct: oxygen, hydrogen, nitrogen, carbon, sulfur, phosphorus, and several metals like gold, silver, copper, iron, mercury, tin, lead, and zinc. Some were wrong. He included light and caloric, which he thought of as a heat substance. But the approach was right. He was building the first real inventory of the building blocks of matter, based on experimental evidence rather than philosophical speculation. And here's the part of the story that still stings. Lavoisier wasn't just a chemist. He was also a tax collector, a member of the Ferme Générale, the private company that collected taxes on behalf of the French crown. It made him wealthy, and it funded his elaborate laboratory. But when the revolution came, and the terror followed, being a former tax collector was essentially a death sentence. Lavoisier was arrested, tried by a revolutionary tribunal, and on May 8, 1794, he was guillotined. The trial lasted a day. The mathematician Joseph Louis Lagrange reportedly said afterward, "It took them only an instant to cut off his head, and 100 years might not suffice to reproduce its like." He was 50 years old, the greatest chemist in the world, dead because of politics. And the science continued without him, as science always does. But you can't help wondering what he might have discovered if he'd had another 20 or 30 years. And here's something that adds another layer of tragedy to Lavoisier's story. Before his arrest, he had been doing some of his most visionary work. He was building better and better analytical tools, refining his list of elements, pushing chemistry further and further from its alchemical roots toward the precise, quantitative science it would become. He was also deeply involved in reforming the French system of weights and measures, the project that would eventually produce the metric system. The metric system, the foundation of scientific measurement worldwide, and Lavoisier was one of its architects. Then the revolution took his head. The mathematician and astronomer Jean-Baptiste Delambre, who continued the metric project after Lavoisier's death, worked for years to complete what Lavoisier had helped start. And every time a scientist anywhere in the world measures something in grams or liters or meters, they're using a system that Lavoisier helped create, even though he didn't live to see it adopted. But chemistry didn't die with Lavoisier. It never does. That's one of the remarkable things about science. It's bigger than any one person, and the questions it raises outlive everyone who asks them. The next great chapter in the story, the one that would eventually lead to the periodic table itself, was about to begin, driven by a question that Lavoisier's list of elements inevitably raised. You've got 33 elements. Fine. But is there a pattern? Is there some deeper order hiding in this list? Some relationship between the elements that would tell you not just what they are, but why they behave the way they do? That question would consume the next 80 years of chemistry. And the first person to make serious progress on it was about as unlikely a candidate as you could imagine. A Quaker schoolteacher from the north of England, colorblind, largely self-taught, with no university degree and no laboratory to speak of. His name was John Dalton, and what he lacked in resources, he more than made up for in sheer stubborn brilliance. And here's a wonderful biographical detail. Dalton was colorblind, red-green colorblind, specifically, a condition that's now sometimes called Daltonism in his honor. He was one of the first people to scientifically describe colorblindness, publishing a paper on it in 1794. He thought the vitreous humor in his eyes might be tinted blue, filtering out certain wavelengths. He was wrong about the mechanism. It's actually about the cone cells in the retina. But he was right that the condition was real and physiological, not imaginary. He was so interested in the question that he left instructions for his eyes to be examined after his death. They were, and the preserved eyes were kept at the Manchester Literary and Philosophical Society for over a century. In the 1990s, DNA from the preserved eyes confirmed that Dalton had a specific genetic mutation affecting the green-sensitive photopigment. The man who couldn't see colors correctly helped us understand why, and he did it by treating his own impairment as a scientific problem rather than a personal shortcoming. Dalton was born in 1766 in Eaglesfield, a tiny village in Cumberland, in the northwest of England. His family were weavers, devout Quakers, and not wealthy. He started teaching at the local Quaker school when he was 12 years old. 12, because the previous teacher had left, and Dalton was apparently the best educated person available. Think about that. A 12-year-old standing in front of a class of children, some of them older than him, teaching arithmetic and reading. He later moved to a school in Kendal, and eventually to Manchester, where he spent most of his adult life, teaching and conducting research at what would become the Manchester Literary and Philosophical Society. Dalton's great contribution was atomic theory. Now, the idea of atoms, indivisible basic units of matter, goes all the way back to the ancient Greek philosopher Democritus, around 400 BCE. Democritus imagined that if you kept cutting a piece of matter in half, eventually you'd reach a particle so small it couldn't be divided further. He called these particles atomos, uncuttable. But Democritus couldn't prove it, and Aristotle dismissed the idea, so it languished for 2,000 years as a philosophical curiosity rather than a scientific theory. Dalton turned it into science. In the first decade of the 1800s, he proposed that each chemical element consists of identical atoms, that atoms of different elements have different weights, and that chemical compounds are formed when atoms combine in simple whole number ratios. Hydrogen atoms all weigh the same. Oxygen atoms all weigh the same, but they're heavier than hydrogen atoms. Water is formed when two hydrogen atoms combine with one oxygen atom. It's beautifully simple, and it explained an enormous amount of chemical data that had been accumulating for decades. And here's the piece that matters most for our story. If different elements have atoms of different weights, then you can assign a number to each element, its atomic weight, relative to some standard. Dalton chose hydrogen, the lightest element, as his baseline, giving it a weight of 1. And then he tried to figure out the relative weights of all the other elements by analyzing chemical compounds and working backward. If water is made of hydrogen and oxygen, and you know the ratio by weight, you can calculate how heavy an oxygen atom is relative to hydrogen. Now, Dalton got some of these numbers wrong, partly because he made incorrect assumptions about the formulas of compounds. He assumed water was one hydrogen atom and one oxygen atom, when it's actually two hydrogens and one oxygen. So his weight for oxygen came out at about 7 or 8 instead of the correct 16. But the method was right. The idea was right. And other chemists quickly took up the project, refining the measurements, correcting the formulas, and gradually building up a more and more accurate table of atomic weights. One of the most important figures in this effort was a Swedish chemist named Jöns Jacob Berzelius, who between about 1810 and 1830 determined the atomic weights of dozens of elements with remarkable accuracy, using meticulous gravimetric analysis, painstakingly weighing reactants and products to many decimal places. Berzelius also gave us the modern system of chemical symbols, H for hydrogen, O for oxygen, Fe for iron, from the Latin ferrum, which is why some of the symbols on the periodic table don't match the English names. Au for gold comes from aurum. Ag for silver comes from argentum. Pb for lead comes from plumbum, which, fun fact, is also where we get the word plumber, because the Romans used lead pipes for plumbing, which turned out to be a terrible idea for entirely different reasons. But that's another story. By 1860, the situation had become so confused, different chemists using different atomic weights, different formulas for the same compounds, different systems of notation, that an international congress was called in Karlsruhe, Germany, to try to sort things out. This was the first International Chemistry Conference, and it's a pivotal moment in our story. The Italian chemist Stanislao Cannizzaro distributed a pamphlet at the Congress explaining how to determine atomic weights correctly using Avogadro's hypothesis, the idea that equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. Canizzaro's arguments were compelling, and they convinced many of the attendees. Among those attending was a young Dmitry Mendeleev, who later said that the Karlsruhe Congress was a turning point in his thinking. The standardized atomic weights that emerged from the Congress were exactly what Mendeleev would need, 9 years later, to construct his periodic table. So by the mid-1800s, you have maybe 60-some elements that have been identified and characterized, each with a measured atomic weight. And chemists are starting to notice something. There seem to be patterns, groups of elements that behave similarly, families with shared properties. The first person to notice this in a systematic way was a German chemist named Johann Wolfgang Dobereiner. Around 1817, Dobereiner pointed out that certain elements seemed to come in groups of three, which he called triads. In each triad, the three elements had similar chemical properties, and the atomic weight of the middle element was approximately the average of the other two. Take lithium, sodium, and potassium. All three are soft, silvery metals that react violently with water. Lithium's atomic weight is about 7, potassium's is about 39, and sodium is right there in the middle at about 23, almost exactly the average of 7 and 39. Or take chlorine, bromine, and iodine, all halogens, all reactive nonmetals with similar chemistry. Chlorine weighs about 35, iodine about 127, and bromine sits at about 80, very close to the average. This was tantalizing. It hinted at an underlying order, but Dobereiner couldn't extend it to all the elements, and most chemists at the time regarded his triads as interesting curiosities rather than evidence of a deep law. The pattern was there, but it was fragmentary. The full picture hadn't emerged yet. About 40 years later, in 1862, a French geologist named Alexandre-Émile Béguier de Champcourtois made another attempt. He plotted the elements on a cylinder according to their atomic weights, wrapping them around in a spiral, and noticed that elements with similar properties often lined up vertically. They appeared at regular intervals along the spiral. He called it the telluric screw, after the element tellurium. It was actually a pretty good insight. But de Champcourtois was a geologist, not a chemist, and his paper was published without the crucial diagram of his spiral, which made it nearly impossible to understand. Hardly anyone noticed it. It vanished into obscurity, which is a shame, because he was genuinely onto something. And then came a moment that's almost painful in hindsight. One of those stories in science where someone is right, and everyone laughs at them, and it takes decades for the laughter to turn into recognition. This is the story of John Newlands. Newlands was an English chemist born in 1837, the son of a Presbyterian minister. He fought as a volunteer with Garibaldi in the Italian Unification Wars, which is a fantastic biographical detail that has absolutely nothing to do with chemistry, but it tells you something about the man's character. He was adventurous, unconventional, willing to stick his neck out. And in 1865, he published a paper proposing what he called the law of octaves. He arranged the known elements in order of atomic weight and noticed that every eighth element seemed to have similar properties, like the notes on a musical scale, where the eighth note is a repetition of the first, just an octave higher. Hydrogen, lithium, sodium, 1, 3, 11, all in the same family, recurring at intervals of roughly 7 elements. It was a real pattern. It was, in essence, the periodicity that gives the periodic table its name. But Newlands made the mistake of presenting it to the Chemical Society in London in 1866, and the reception was brutal. One prominent chemist supposedly asked, with withering sarcasm, whether Newlands had tried arranging the elements alphabetically and looked for patterns that way. The Chemical Society actually refused to publish his paper. They thought it was numerological nonsense, pattern hunting and random data. Newlands was devastated. He continued his work as a sugar chemist, largely forgotten by the scientific mainstream. It wasn't until 1887, over 20 years later, that the Royal Society finally awarded him the Davy Medal, acknowledging his contribution. By then, another man had gotten the credit for doing what Newlands had almost done. And this is one of those moments in science that should make you a little uneasy, because it shows you how much progress depends on reception, on timing, on the politics of who gets heard and who gets dismissed. Newlands was right. He was substantially right. The pattern he identified, periodicity, the regular recurrence of chemical properties at fixed intervals, was the central insight of the periodic table. He just didn't present it in a way that the establishment could accept. Maybe his data was a little too messy. Maybe his comparisons to music seemed fanciful. Maybe he was simply not famous enough, not well connected enough, not persuasive enough. Science is supposed to be about the ideas, not the person. But in practice, the person matters enormously. How you present an idea, where you publish it, who your supporters are, whether the establishment is ready to hear it, all of that affects whether a discovery is celebrated or ignored. Newlands eventually got his recognition, but too late to matter for his career. And the man who did get the credit, the man whose name you probably know, was working 1,000 miles to the east, in St. Petersburg, Russia, and he was about to achieve something that would put his name on the walls of chemistry classrooms forever. Dmitry Ivanovich Mendeleev. Even the name has a kind of weight to it, doesn't it? He's one of those figures who looms so large in the history of science that it's easy to forget he was a real person, with a real life, and a genuinely extraordinary one at that. So let's slow down here and get to know him, because his story is worth telling properly. Mendeleev was born on February 8, 1834, in Tobolsk, Siberia. And when I say Siberia, I want you to feel the remoteness of that. Tobolsk was a provincial town in western Siberia, thousands of miles from Moscow and St. Petersburg, deep in the vast Russian interior. It was cold, isolated, and about as far from the centers of European science as you could get, while still being in the Russian Empire. His father, Ivan, was the director of the local gymnasium, a secondary school, but went blind from cataracts early in Dmitry's childhood and had to give up his position. The family's income collapsed. Dmitry's mother, Maria, a remarkably determined woman, reopened a glass factory that had belonged to her family and ran it to support her children. There were 17 children in the family, though not all survived childhood. Dmitry was the youngest. When Mendeleev was 13, his father died. When he was 15, the glass factory burned down. Maria, undaunted, decided that her youngest son was going to get a proper education, and she packed up what was left of the family and traveled, on horseback and by coach, across the vast Russian landscape, all the way to Moscow, a journey of well over 1,000 miles. Moscow turned out to be a dead end. The university wouldn't admit Dmitry, so Maria pressed on to St. Petersburg, another 400 miles, and managed to get him into the main pedagogical institute where his father had studied. It was not a prestigious institution. It was not where the children of the aristocracy went, but it was a real education, and Mendeleev seized it. Maria died shortly after getting him enrolled. She had essentially spent the last of her strength getting her son to school. Mendeleev never forgot it. By all accounts, he carried his mother's memory with him his entire life, and the determination she modeled, that fierce, refuse-to-quit stubbornness, became one of his defining characteristics. At the Pedagogical Institute, Mendeleev studied chemistry and physics, and he quickly showed himself to be brilliant, if somewhat unruly. He graduated first in his class, despite battling tuberculosis. He was actually told by doctors that he might not survive, and he spent time convalescing in Crimea, but he recovered, and after teaching for a while, he won a government fellowship to study abroad. He went to Heidelberg, Germany, where he worked in the laboratory of Robert Bunsen. Yes, that Bunsen, the one with the burner, and attended lectures by other leading European chemists. He came back to Russia more determined than ever to build a world-class chemistry program in his own country. By 1867, Mendeleev was a professor at the University of St. Petersburg, and he was writing a textbook, Principles of Chemistry. And this is where the periodic table enters the story, because the table wasn't born out of abstract theorizing. It was born out of a very practical problem. Mendeleev needed to figure out how to organize his textbook. He had to decide what order to discuss the elements in. And as he thought about that organizational problem, something deeper started to emerge. Here's what he did. He wrote the name and properties of each known element on a separate card, like playing cards. 63 elements, 63 cards. And then he started arranging them, sorting them, grouping elements with similar properties together, laying them out in order of increasing atomic weight. And what he found, when he did this carefully and systematically, was a pattern. When you arrange the elements by weight, properties repeat at regular intervals. Light, reactive metals show up, then less reactive elements, then nonmetals, then a very reactive nonmetal, and then back to a light, reactive metal again. A periodic recurrence, like a musical theme that repeats with variations. Now, here's the legend, and I want to be careful about this because it may be embellished. The story goes that on the night of February 17, 1869, Mendeleev had been working furiously on his arrangement, shuffling his cards, trying different configurations. He'd worked all day and into the evening, and at some point, he fell asleep at his desk and had a dream. In the dream, he saw the elements falling into place in a table, rows and columns, everything clicking into a grid. He woke up and wrote it down. Whether the dream really happened is debated. Some historians think Mendeleev himself promoted the story later because it made for a good narrative. Others think it's probably based in truth, the kind of subconscious pattern recognition that can happen when you've been obsessing over a problem for weeks. Either way, what matters is what he produced. On March 6, 1869, a colleague presented Mendeleev's paper to the Russian Chemical Society. The paper included a table arranging all 63 known elements, and it was, with some modifications, recognizably, the periodic table we use today. But here's the thing that separates Mendeleev from everyone who came before him, from Dobereiner and de Champ-Courtois and Newlands, and all the others who had glimpsed pieces of the pattern. Mendeleev didn't just organize the known elements. He noticed that for the pattern to work properly, there had to be gaps, places in the table where an element should exist but hadn't been discovered yet. And instead of treating those gaps as problems or ignoring them, he treated them as predictions. Think about how bold that is. He was saying, in effect, I trust this pattern so much that I'm willing to tell you exactly what the undiscovered elements will look like. He described 3 of these missing elements in remarkable detail. For the element he called Eka aluminum, Eka meaning one beyond in Sanskrit, he predicted it would be a soft metal with a density of about 5.9, a low melting point, and an atomic weight around 68. For Eka boron, he predicted specific oxide formulas and chemical behaviors. For Eka silicon, he predicted the density, the atomic weight, the color, the behavior in acids, and then chemistry went out and found them. In 1875, a French chemist named Paul-Émile Lecoq de Boisbaudran discovered a new element in zinc ore from the Pyrenees. He named it gallium, after Gallia, the Latin name for France. And when he measured its properties, density 5.91, melting point about 30 degrees Celsius, so low that it melts in your hand, they matched Mendeleev's predictions almost exactly. There's actually a wonderful story here. Lecoq initially measured gallium's density at 4.7, which didn't match Mendeleev's prediction of 5.9. Mendeleev, from St. Petersburg, essentially told the French chemist that his measurement must be wrong, and when Lecoq purified his sample further and remeasured, he got 5.91. Mendeleev had been more right about an element he'd never seen than the man who'd actually discovered it. That takes an almost unreasonable amount of confidence. Then, in 1879, Lars Fredrik Nilsson in Sweden discovered scandium, Mendeleev's Eka boron, and its properties matched the predictions beautifully. And in 1886, Clemens Winkler, in Germany, discovered germanium, Eka silicon, and the match was almost uncanny. The density, the atomic weight, the color, the specific heat, the formulas of its compounds, all of it predicted years in advance by a Siberian chemist working with nothing but a set of cards and a deep conviction that nature has a pattern. That's the moment when the scientific world truly took notice. Predictions that come true are the gold standard of science. Anyone can organize existing data in a pattern, but when your pattern tells you something nobody knew yet, and then it turns out to be right, that's when a pattern becomes a law. Mendeleev went from being one of many chemists tinkering with element arrangements to being the man who had decoded the fundamental organization of matter. And here's a detail I love about Mendeleev himself. He was not a polished, refined establishment figure. He was, by many accounts, a large, somewhat wild-looking man with an enormous mane of hair that he refused to cut more than once a year, regardless of social expectations. He was passionate, argumentative, and deeply unconventional. He eventually divorced his first wife and married a much younger art student, which caused a scandal in Russian society. When someone pointed out that he was technically a bigamist since his divorce hadn't been officially processed, Tsar Alexander III reportedly waved it away, saying, "Mendeleev may have 2 wives, but I have only one Mendeleev." Whether that quote is exactly accurate is debatable, but it captures the esteem in which he was held. He was simply too important, too brilliant, too useful to Russia to be subjected to the usual social consequences. And Mendeleev wasn't just a chemist. He was involved in Russian industry, agriculture, and oil production. He advised the government on tariff policies. He developed improved methods for refining petroleum. He was, in many ways, the kind of scientist who saw no boundary between pure research and practical application. The kind of person who could discover the fundamental organization of the elements and also figure out better ways to drill for oil. He lived and breathed chemistry in a way that permeated every aspect of his life. Now I should mention that Mendeleev was not the only person working on this. A German chemist named Lothar Meyer had independently developed a very similar table around the same time. Meyer published a version in 1864 that was less complete, and a fuller version in 1870, a year after Mendeleev's. Meyer's table was in many ways equally insightful. He particularly emphasized how physical properties, like atomic volume, varied periodically with atomic weight, and his graphical representation of this was beautiful. But Meyer hadn't made predictions. He hadn't left gaps. He'd organized the known elements elegantly, but he hadn't stuck his neck out and said, "Here's what we haven't found yet." And in science, as in life, the person who makes the bold prediction and gets it right gets the credit. Mendeleev made the bold prediction. Meyer acknowledged it graciously. Both men received the Davy Medal from the Royal Society in 1882. Mendeleev 1 year, Meyer the next. But history remembers Mendeleev, and there's a certain justice in that. So by the 1880s, the periodic table exists. It works. It predicts. But it's not perfect, and Mendeleev knew it. There were awkward spots where he had to put a heavier element before a lighter one to make the chemistry work out right. Tellurium and iodine, for instance. Tellurium is heavier than iodine, but Mendeleev placed tellurium first because its chemistry clearly put it in the same family as sulfur and selenium, not with the halogens. He was right to do that, but he didn't know why the weight ordering was wrong. That mystery wouldn't be resolved for another 25 years, and its resolution would require an entirely new understanding of what atoms actually are. But before we get there, there's another chapter of the story that deserves its own slow telling, because it involves one of the most remarkable discoveries in the history of chemistry. the discovery of a whole family of elements that nobody had even suspected existed, elements so aloof, so supremely indifferent to the rest of the periodic table, that they'd been hiding in plain sight for millions of years. I'm talking about the noble gases, and their discovery is one of my favorite stories in all of science, because it starts with a discrepancy so tiny that most people would have ignored it, and it ends with an entirely new column being added to the periodic table. It's a story about the power of paying attention. It starts in the 1890s with a British physicist named John William Strutt, better known as Lord Rayleigh. Rayleigh was a meticulous experimenter, the kind of person who would measure something 10 times, then 10 more times, then worry that his apparatus might have a systematic error. And he'd been measuring the density of nitrogen. Simple enough, right? Take nitrogen from the air, weigh it, compare it to nitrogen produced by chemical decomposition of nitrogen-containing compounds. The two should be the same. They weren't. The nitrogen extracted from air was consistently, stubbornly, heavier than the nitrogen made by chemical reactions. Not by much. The difference was tiny, about 1 part in 200, roughly 0.5%. Most scientists would have chalked it up to experimental error and moved on. Rayleigh didn't. He published a note in the journal Nature in 1892, essentially asking, "Does anyone know why atmospheric nitrogen is slightly heavier than chemical nitrogen? Can anyone explain this?" A Scottish chemist named William Ramsay saw Rayleigh's note and got interested. Ramsay suspected that atmospheric nitrogen might contain a small admixture of some heavier, unknown gas, so he devised an experiment to find out. He took a sample of atmospheric nitrogen and systematically removed the nitrogen from it by passing it over hot magnesium, which reacts with nitrogen to form magnesium nitride. If the sample was pure nitrogen, it should all react and nothing would be left. But something was left. About 1% of the original sample remained as a gas that refused to react with anything. Ramsay tested it with everything he could think of: hot metals, strong acids, electric sparks, and nothing worked. The gas was completely inert. It simply would not combine with anything. Rayleigh and Ramsay announced their discovery jointly in 1894. They named the new element argon, from the Greek word argos, meaning lazy or idle, because that's essentially what it was, a gas that just sat there, chemically doing absolutely nothing. Now, here's the interesting problem this created. Where do you put argon on the periodic table? It had an atomic weight of about 40, which placed it between potassium at 39 and calcium at 40. But argon didn't behave like anything on the table. It had no chemical properties to speak of. It didn't form compounds. It didn't react. Mendeleev was skeptical. He initially suggested that argon might not be a true element at all, but perhaps a heavier form of nitrogen, N3 instead of N2. He was wrong about that, but his instinct that argon didn't fit the existing table was understandable. The table had no room for an element with no chemistry, but Ramsay wasn't done. He suspected that if one inert gas existed, there might be others, and between 1895 and 1898, he and his collaborators discovered 4 more. First came helium in 1895. Now, helium had actually been detected spectroscopically in the Sun back in 1868. The astronomer Joseph Norman Lockyer had noticed an unfamiliar yellow spectral line during a solar eclipse and proposed a new element, naming it helium after Helios, the Greek word for sun. But nobody had found it on Earth. Ramsay did, isolating it from a uranium mineral called cleveite. Then, in 1898, working with a colleague named Morris Travers, Ramsay discovered 3 more: neon, krypton, and xenon. Neon, from the Greek neos, meaning new. Krypton, from kryptos, hidden. Xenon, from Xenos, strange or foreign. These names alone tell you something about the delight these scientists took in their work. They were naming elements the way you might name characters in a story, each name capturing something essential about the element's character. All of them completely inert, all of them gases, and all of them, Ramsey realized, formed a coherent group, a whole new column on the periodic table, sitting between the halogens and the alkali metals. Ramsey got the Nobel Prize in Chemistry in 1904 for this. Rayleigh got the Nobel Prize in Physics the same year. They were the right prizes for the right people. Rayleigh for the physical measurement that started it all. Ramsey for the chemical detective work that finished it. And the periodic table gained a new family, Group 18, the noble gases, sitting proudly at the far right of the table. A family of elements so stable, so self-contained, so satisfied with their own electron configurations that they wanted nothing to do with anyone else. And here's why that matters. Beyond just adding a column, the noble gases revealed something fundamental about the structure of the periodic table itself. Their extreme stability, their refusal to form chemical bonds, would later be understood as a consequence of having completely filled electron shells. They have the maximum number of electrons that their outermost shell can hold, and that completeness makes them energetically satisfied. They don't need to gain or lose or share electrons with other atoms, because they're already in their lowest energy configuration. And that insight, that chemical behavior, is determined by electron configuration, by how many electrons an atom has and how they're arranged. That's the key to understanding why the periodic table has the shape it does. But that understanding required knowing about electrons, and in the 1890s, the electron hadn't even been discovered yet. Well, actually, it was about to be, because right around the same time Ramsey was chasing noble gases, another experiment was happening in a laboratory in Cambridge, England. J.J. Thomson, working at the Cavendish Laboratory, was studying cathode rays, mysterious beams produced when you run an electric current through a vacuum tube. And in 1897, Thomson showed that these rays were made of tiny particles, much smaller than atoms, carrying a negative electric charge. He called them corpuscles. We call them electrons. And their discovery blew apart the idea that atoms were indivisible. They had parts. They had internal structure. The word atom, uncuttable, was suddenly deliciously wrong. But Thomson's discovery raised as many questions as it answered. If atoms contain these tiny negative particles, what else is in there? Where does the positive charge live? Thomson proposed his plum pudding model, electrons embedded in a diffuse sphere of positive charge, like raisins in a pudding. And then Rutherford's gold foil experiment in 1909 demolished that picture and revealed the nucleus, a tiny, dense core containing virtually all the atom's mass. And then Niels Bohr came along with his quantum orbits. We talked about all of this in the context of quantum physics, but here, what matters is how it connects to the periodic table. Because once you understand the internal structure of the atom, the nucleus with its protons and neutrons, the electrons arranged in shells and subshells, the periodic table stops being a mysterious pattern and starts being an inevitable consequence of atomic physics. And the person who made that connection, who showed that the fundamental organizing principle of the periodic table isn't atomic weight but atomic number, the number of protons in the nucleus, was a young English physicist whose life was tragically, heartbreakingly short. His name was Henry Moseley, and his story is one that deserves to be far better known than it is. Henry Gwyn Jeffreys Moseley was born in 1887 in Weymouth, on the southern coast of England. His father was a professor of anatomy at Oxford, and his grandfather had been a distinguished naturalist. Science ran in the family. Young Henry was brilliant, studious, and by all accounts rather serious. He went to Eton, then to Oxford, where he studied physics, and in 1910 he moved to Manchester to work in Ernest Rutherford's laboratory. And it was there, between 1913 and 1914, that he did the work that changed the periodic table forever. Here's the problem Moseley was attacking. Mendeleev had arranged the elements by atomic weight, and it worked, mostly. But there were those nagging exceptions: tellurium and iodine, cobalt and nickel, argon and potassium. In each case, the element with the heavier atomic weight had to be placed before the lighter one to keep the chemistry consistent. Mendeleev had simply overridden the weight ordering when it conflicted with the chemical properties, and that was a reasonable, pragmatic choice, but it was intellectually unsatisfying. There had to be a deeper reason why the weight ordering sometimes failed. Moseley found it. What he did was shoot beams of electrons at samples of different elements and measure the X-rays that came off. Each element produced X-rays at characteristic frequencies, and Moseley discovered that when you plotted the square root of those frequencies against the position of the element in the periodic table, you got an almost perfectly straight line. Not almost perfectly. The relationship was stunningly precise. And the crucial insight was this: the quantity that determined the X-ray frequency wasn't the atomic weight. It was the atomic number, the number of positive charges in the nucleus, which we now know is the number of protons. Moseley showed that the true organizing principle of the periodic table is atomic number, not atomic weight. When you arrange elements by atomic number instead of weight, all the awkward exceptions vanish. Tellurium, atomic number 52, comes before iodine, atomic number 53, even though tellurium is heavier. Cobalt, 27, comes before nickel, 28. Argon, 18, comes before potassium, 19. The chemistry lines up perfectly because chemical properties depend on electrons. The number of electrons equals the number of protons, and the number of protons is the atomic number. Everything clicks into place. Moseley's work also did something else that was enormously important. By plotting his straight line and looking for gaps, he could tell exactly how many elements were missing from the table and what their atomic numbers had to be. In 1913, several elements between aluminum and gold had not yet been discovered. Moseley's line showed precisely where the gaps were, at atomic numbers 43, 61, 72, and 75. He was mapping the table's blank spaces with the precision of a surveyor marking where houses should be built on a new street. This was brilliant. This was the kind of work that wins Nobel Prizes, and there is every reason to believe that Moseley would have received one, probably quite soon, if he had lived. But Moseley was young, idealistic, and British, and it was 1914. World War I broke out. Despite Rutherford's efforts to keep him in the laboratory, despite his obvious value to science, Moseley volunteered for military service. He was commissioned as a lieutenant in the Royal Engineers and sent to Gallipoli. On August 10, 1915, during the disastrous Gallipoli campaign, Henry Moseley was shot through the head by a sniper while communicating by telephone during the Battle of Chunuk Bair. He was 27 years old. His death was one of the great losses of 20th century science. It's hard to overstate how much he might have accomplished. He was doing work of Nobel caliber at 25. He had already fundamentally changed how we understand the periodic table. The British government, partly in response to Moseley's death, later adopted a policy of not allowing prominent scientists to serve in combat roles. That came too late for Moseley. But his work lived on. Atomic number, the simple count of protons in the nucleus, became the organizing principle of the periodic table. And once you combine that with the emerging understanding of electron shells and quantum mechanics, the entire structure of the table becomes clear. Let's take a moment with that, because it's really satisfying when you see it. Think about it this way. Every atom has a nucleus surrounded by electrons, and those electrons don't just float around randomly. They arrange themselves in shells, energy levels, and each shell can hold a specific maximum number of electrons. The first shell can hold 2. The second can hold 8. The third can hold 18, though in practice, it often fills in stages. These numbers come directly from quantum mechanics, from the solutions to Schrödinger's equation for electrons in a central potential. Now, here's the key. The chemical properties of an element, how it reacts, what compounds it forms, whether it's a metal or a nonmetal, whether it's reactive or inert, are determined almost entirely by the electrons in its outermost shell. These are called valence electrons, and they're the ones that participate in chemical bonding. Elements with the same number of valence electrons behave similarly. That's why the periodic table works. The periodicity, the repeating pattern of properties, happens because as you add more and more electrons to atoms of increasing atomic number, the outermost shell fills up, and then a new shell starts. Each time a new shell starts, the chemical properties reset, and you're back to something that behaves like the beginning of the previous row. Hydrogen has 1 electron in its first shell. Helium has 2. The first shell is full, so helium is a noble gas. Lithium has 3 electrons, 2 in the first shell, 1 starting the second, so lithium behaves like a more complicated version of hydrogen, a reactive metal. Go across the second row, adding electrons 1 by 1. Beryllium with 2 in the outer shell, boron with 3, carbon with 4, nitrogen with 5, oxygen with 6, fluorine with 7, and neon with 8. The second shell is full, and neon is another noble gas. Then sodium starts the third row, with 1 electron in the third shell, and the pattern repeats. That's why sodium and lithium are in the same column. They both have 1 electron in their outermost shell. That's why fluorine and chlorine are in the same column. They both have 7. The table isn't a human invention. Not really. It's a reflection of quantum mechanics. The shape of the table, the 2 short rows at the top, then the 2 longer rows, then the longer rows with the lanthanides and actinides separated at the bottom. All of that reflects the sequence in which electron subshells fill up, which is governed by the energies of the quantum states, which come from the fundamental equations of quantum mechanics. Mendeleev discovered the pattern empirically, by shuffling cards. Moseley showed that atomic number, not weight, is the key, and quantum mechanics explained why. 3 layers of understanding, each one deeper than the last, each one making the table more beautiful. And here's something that I think is genuinely wonderful. Mendeleev, shuffling his cards in St. Petersburg in 1869, was unknowingly arranging the elements according to quantum mechanical principles that wouldn't be discovered for another 50 years. He couldn't have known about electrons, or shells, or quantum numbers. He just saw the pattern. The pattern was real, because quantum mechanics is real, and the periodic table is, in a deep sense, a portrait of quantum mechanics that you can hang on a wall. Now, once the theoretical framework was in place, atomic number, electron shells, quantum mechanics, the table became a powerful predictive tool, not just for missing elements, but for understanding chemical behavior. You could look at an element's position in the table and immediately know quite a lot about it. Elements on the left side tend to lose electrons easily and form positive ions. They're metals. Elements on the right side tend to gain electrons and form negative ions. They're nonmetals. Elements in the middle are the transition metals, with more complex electron configurations and a tendency to form colorful compounds. The noble gases on the far right have full outer shells and resist bonding. The halogens, 1 column to their left, need just 1 more electron to fill their shells, which makes them ferociously reactive. Let me give you a concrete example of how this works. because it's really elegant once you see it. Take the alkali metals: lithium, sodium, potassium, rubidium, cesium, francium. They're all in the first column of the table. They all have one electron in their outermost shell, and because of that single lonely electron, they all share a distinctive set of properties. They're all soft metals. You can cut sodium with a butter knife, which is a bizarre experience if you've ever done it. They all react violently with water. Drop a piece of sodium into water and it fizzes, skitters across the surface, and may actually catch fire. The hydrogen gas produced by the reaction ignites. Drop a piece of cesium into water, and the reaction is so violent, it's essentially an explosion. And the reason the reaction gets more dramatic as you go down the column is that the outermost electron gets farther and farther from the nucleus, held less and less tightly, easier and easier to pull away. Quantum mechanics predicts this. The periodic table shows it, and a chunk of cesium thrown into a lake demonstrates it in a way you'll never forget. Or consider the halogens: fluorine, chlorine, bromine, iodine, astatine. They're in the column second from the right. They all have 7 electrons in their outermost shell, which means they're all 1 electron short of a completely filled shell. They desperately want that 8th electron, and that want makes them ferociously reactive. Fluorine is the most reactive element in the entire periodic table. It will react with almost anything, including glass and platinum, and it was so difficult and dangerous to isolate that several chemists died or were seriously injured trying. Henri Moissan finally isolated it in 1886, and he won the Nobel Prize in Chemistry in 1906, partly for that achievement. The periodic table told you fluorine would be reactive. It didn't tell you it would try to kill anyone who got close. And this is where the table starts connecting to everything else, to materials science, to biology, to geology, to the technology in your pocket right now. Because understanding why elements behave the way they do, understanding their positions in the table, is the foundation of modern chemistry. And modern chemistry is the foundation of, well, practically everything. But there's another part of this story that we haven't touched yet, and it involves a discovery that shook the periodic table to its foundations, challenged the very idea that elements were permanent and unchanging, and opened up an entirely new chapter in the history of science. And it starts with a man who accidentally left a photographic plate in a drawer next to some uranium ore, and the woman who followed that accident all the way to a discovery that would change the world. That man was Henri Becquerel, and the year was 1896. Becquerel was a French physicist who came from a dynasty of scientists. His father and grandfather had both been physics professors and had both studied phosphorescence, the phenomenon where certain materials glow after being exposed to light. Becquerel was continuing the family tradition, and after Wilhelm Röntgen's sensational discovery of X-rays in late 1895, Becquerel had a hypothesis. Maybe phosphorescent materials produce X-rays when they glow, so he took some uranium salts, which were known to be phosphorescent, placed them on top of a photographic plate wrapped in black paper, and exposed the whole thing to sunlight. When he developed the plate, he found it was fogged, darkened, as if X-rays had passed through the paper and exposed it. His hypothesis seemed confirmed, but then the weather in Paris turned cloudy. Becquerel had prepared another experiment, but couldn't run it because there was no sunlight. He put the uranium salts and the wrapped photographic plate in a drawer and left them there for several days. When he eventually developed the plate, more out of thoroughness than expectation, he found it was fogged again, strongly fogged, even though the uranium hadn't been exposed to sunlight. Even though there'd been no phosphorescence, the uranium was doing something all by itself, in the dark, in a drawer. It was emitting some kind of radiation, spontaneously, without any external energy source. This was radioactivity, though Becquerel didn't use that word yet. It was one of the most consequential accidents in the history of science, right up there with Alexander Fleming noticing that mold had killed the bacteria on his petri dish, which led to penicillin. And it was bizarre. In all of known physics, energy had to come from somewhere. You heated something, you lit it, you dropped it, you ran current through it. Energy didn't just appear from nowhere, but uranium seemed to be radiating energy continuously, without any input, without any apparent source. It was as if it contained an internal, inexhaustible reservoir of energy. Nobody understood it, and this is where Marie Curie enters the story. And honestly, Marie Curie deserves more than a section in a sleepy narration about the periodic table. She deserves the entire night. But let's give her what space we can, because her life and her work are inseparable, and both are extraordinary. Maria Salomea Skłodowska was born in Warsaw, Poland, in 1867, when Poland was under Russian imperial rule. Her family were teachers and intellectuals, but they were not wealthy, and life under Russian occupation was oppressive. Women were not allowed to attend university in Russian-controlled Poland. Marie's older sister, Bronisława, wanted to study medicine in Paris, but the family couldn't afford to send her. So Marie made a deal with her sister. She would work as a governess and send money to support Bronisława's studies in Paris. And then, when Bronisława was established, she would help Marie come to Paris and study in turn. For several years, that's what Marie did. She worked as a governess in the Polish countryside, teaching children of wealthy families, saving what she could, studying mathematics and physics on her own at night by candlelight. It was isolating and often miserable. But in 1891, at the age of 24, she finally made it to Paris, enrolling at the Sorbonne. She was one of a tiny number of women in the science faculty. She lived in a garret apartment so cold that the water in her wash basin sometimes froze overnight. She ate so little that she occasionally fainted in class. But she graduated first in her physics degree in 1893 and second in mathematics the following year. In 1894, she met Pierre Curie, a French physicist who was already doing distinguished work on magnetism and crystallography. Pierre was quiet, idealistic, somewhat unworldly, the kind of scientist who could forget to eat because he was thinking about symmetry. They fell in love over science. Marie later wrote that she was drawn to Pierre because of his dedication to research and his complete indifference to personal fame. They married in 1895 and formed one of the most productive scientific partnerships in history. After Becquerel's discovery of uranium's strange radiation, Marie decided to make it the subject of her doctoral research. It was a bold choice. The phenomenon was brand new, barely understood, and most established physicists hadn't even decided if it was interesting. Marie thought it was very interesting. She began by systematically testing every element she could get her hands on, looking for others that emitted this penetrating radiation, and she found one, thorium. The radiation wasn't unique to uranium. It was a property of certain heavy elements. Marie coined the word radioactivity to describe it. But then she noticed something that didn't make sense. When she tested a uranium ore called pitchblende, the radiation it emitted was significantly stronger than what pure uranium alone could account for. The ore was more radioactive than the uranium in it, which meant there had to be something else in the pitchblende, something even more radioactive than uranium, present in very small quantities. And so began one of the most physically grueling research campaigns in the history of science. Marie and Pierre, working in a converted shed at the School of Physics and Chemistry in Paris, a shed with a leaky glass roof, a dirt floor, and almost no equipment, set about extracting this unknown substance from tons of pitchblende ore. Literally tons. The unknown element was present in such minute quantities that they had to process enormous volumes of ore, dissolving it in acid, precipitating it, filtering it, crystallizing it, over and over and over, in an exhausting cycle of physical and chemical labor that went on for months, then years. In July 1898, they announced the discovery of a new element. Marie named it polonium, after her homeland of Poland, which was still struggling under foreign rule. It was a political statement embedded in a scientific paper, and it was deliberate. And then, in December 1898, they announced a second new element, radium. Radium turned out to be astonishingly radioactive, millions of times more so than uranium. A speck of radium salt glowed in the dark with an eerie blue-green light. It warmed itself, measurably, from the energy of its own radioactive decay. It was the most remarkable substance anyone had ever encountered. It took the Curies 4 more years of backbreaking labor to isolate enough pure radium to determine its atomic weight and confirm it as a true element. Marie's doctoral thesis, presented in 1903, described this work, and it's considered one of the most important doctoral theses in the history of science. That same year, Marie and Pierre Curie, along with Henri Becquerel, were awarded the Nobel Prize in Physics for their work on radioactivity. Marie was the first woman to receive a Nobel Prize, but the story doesn't end there, and much of what comes next is painful. In 1906, Pierre was killed in a traffic accident on a rainy Paris street, struck by a horse-drawn cart. Marie was devastated. She took over his professorship at the Sorbonne, the first woman to hold a professorship there, and continued their research alone. In 1911, she received a second Nobel Prize, this time in chemistry, for her discovery and isolation of polonium and radium. She remains the only person to have won Nobel Prizes in 2 different sciences. But Marie Curie's work killed her. Nobody understood the dangers of radiation in those early years. Marie handled radioactive substances with her bare hands. She carried test tubes of radioactive isotopes in her pockets. Her personal effects, her notebooks, her cookbooks, even her furniture, are still so radioactive that they're kept in lead-lined boxes at the Bibliothèque Nationale de France, and you have to sign a liability waiver to access them. They will remain dangerously radioactive for another 1,500 years. Marie Curie died on July 4, 1934, of aplastic anemia, her bone marrow destroyed by decades of radiation exposure. She was 66 years old. Her daughter Irène Joliot-Curie would continue the family's tradition of nuclear research and, together with her husband Frédéric, discover artificial radioactivity, showing that you could make stable elements radioactive by bombarding them with alpha particles. Irène and Frédéric won the Nobel Prize in Chemistry in 1935 for this work, and Irène, like her mother, died from the effects of radiation exposure, of leukemia, in 1956. The Curie family paid for their discoveries with their bodies. In 1995, Marie Curie's remains were moved to the Panthéon in Paris, the resting place of France's most honored citizens. She was the first woman to be interred there on her own merits. Element 96, curium, was named in honor of both Marie and Pierre. It sits in the actinide series, among the elements that exist because of the nuclear transformations Marie first studied. It seems fitting. Now, the reason radioactivity matters so deeply for the story of the periodic table is this. It showed that elements are not permanent. They change. They transmute. A uranium atom, over time, decays into a whole chain of other elements: thorium, radium, radon, polonium, and eventually lead. The alchemist's dream of transmutation was real, just not in the way they imagined. Elements don't transform because you mix them with magical substances. They transform because their nuclei are unstable, because the forces holding those protons and neutrons together aren't quite strong enough, and so the nucleus sheds particles, alpha particles, beta particles, gamma rays, and becomes a different element in the process. Radium isn't just sitting there glowing. It's dying. Its atoms are disintegrating, one by one, each one becoming something else. And this process, radioactive decay, follows a precise mathematical law. Each radioactive isotope has a half-life, a characteristic time after which exactly half of a given sample will have decayed. For radium-226, that half-life is about 1,600 years. For uranium-238, it's about 4.5 billion years, close to the age of the Earth itself, which is why there's still uranium in the ground. For some isotopes, the half-life is fractions of a second. The atom comes into existence and is gone almost before you can measure it. This discovery, radioactive decay, also gave scientists something extraordinarily valuable: a clock. Because each radioactive isotope decays at its own characteristic rate, and that rate never changes, no matter what you do to the material. You can heat it, cool it, crush it, dissolve it in acid. The half-life stays the same, which means that if you find a rock containing a radioactive element and its decay products, you can measure the ratio of parent to daughter atoms and calculate how long the decay has been happening. That's radiometric dating, and it's how we know the age of the Earth, about 4.54 billion years, determined primarily from uranium-lead dating of ancient zircon crystals. It's how we know the age of the oldest rocks, the oldest fossils, the timing of mass extinctions. The periodic table, through radioactive decay, gave us the ability to read deep time itself. And this brings us to a question that would drive the next great chapter in the story of the periodic table. If elements can transform into other elements through radioactive decay, can we make new elements deliberately? Can we build atoms that have never existed in nature? Can we extend the periodic table beyond what the Earth gave us? The answer, as it turns out, is yes. And the story of how we did it involves particle accelerators, a world war, the most destructive weapon ever created, and a lanky American chemist from a small town in Michigan who would end up moving elements around on the periodic table, like a man rearranging furniture in his living room. His name was Glenn Theodore Seaborg, and if you want to understand the modern periodic table, the one hanging on the wall right now, with all those extra rows at the bottom, you need to understand Seaborg, because he reshaped the table more than any single person since Mendeleev. But let's back up a little first, because before Seaborg, someone else made the first truly synthetic element. The first one created in a laboratory rather than found in the Earth. And that story starts with a gap in the periodic table. Remember Moseley's straight line, the one that showed exactly where the missing elements should be? One of those gaps was at atomic number 43. For decades, chemists searched for element 43 in natural minerals. Several people claimed to have found it. None of the claims held up, and eventually, in 1937, two Italian physicists at the University of Palermo, Carlo Perrier and Emilio Segre, figured out why nobody had found it. It doesn't exist in nature, not in any detectable quantity. Every isotope of element 43 is radioactive, with half-lives so short, the longest is about 4 million years, that even if it had been present when the Earth formed, it would have decayed away long ago. Perrier and Segre created element 43 by bombarding a sample of molybdenum, element 42, with deuterons, nuclei of heavy hydrogen, in a cyclotron, a type of particle accelerator invented just a few years earlier by Ernest Lawrence at Berkeley. The resulting nuclear reactions produced atoms with 43 protons, a new element. They named it technetium, from the Greek teknetos, meaning artificial. It was the first element made by human hands rather than found in the ground, and its very existence proved that the periodic table extended beyond what nature provided. There were atoms that could exist, that the laws of physics allowed, but that the universe hadn't bothered to make, or had made and then lost to radioactive decay. Human beings could fill in the blanks. Now, here's where Glenn Seaborg enters the picture. Seaborg was born in 1912 in Ishpeming, Michigan, a small mining town on the Upper Peninsula. His family were Swedish immigrants. His father was a machinist. The family moved to Southern California when Glenn was young, and he grew up in a modest neighborhood near what is now Watts. He was a good student, tall and athletic, and he went to UCLA for college, then Berkeley for his PhD in chemistry. He joined the Berkeley faculty in 1937 and quickly found his calling, nuclear chemistry, the study of atomic nuclei and their transformations. And here's where the story gets really exciting. In 1940, Seaborg and his collaborators at Berkeley created element 94 by bombarding uranium with deuterons. They named it plutonium after the planet Pluto, continuing the naming tradition that had given us uranium after Uranus and Neptunium, element 93, discovered shortly before, after Neptune. Plutonium turned out to be extraordinarily important because one of its isotopes, plutonium-239, was fissile. It could sustain a nuclear chain reaction. And this was 1941. World War II was raging. The Manhattan Project was getting underway, and plutonium-239 became one of the two materials used in the first atomic bombs. Seaborg was recruited into the Manhattan Project and put in charge of the chemistry of plutonium, figuring out how to produce it in quantity, purify it, and handle it. This was challenging on multiple levels, not least because plutonium was a brand new element that had never existed in quantities larger than micrograms, and now they needed kilograms of it for a weapon. Seaborg's team at the University of Chicago's Metallurgical Laboratory developed the chemical separation processes that made it possible. The plutonium for the bomb dropped on Nagasaki on August 9, 1945, was produced using processes Seaborg helped design. The moral weight of that work stayed with Seaborg for the rest of his life, as it did with many Manhattan Project scientists. But there's another aspect of his wartime work that matters more for the story of the periodic table. As Seaborg and his colleagues created and studied one new element after another, neptunium, plutonium, and then americium and curium during the war, they noticed something puzzling. These new heavy elements didn't behave the way the periodic table predicted. According to the table as it was then arranged, elements 89 through 103 should be transition metals, continuing the pattern of the sixth row. But the chemistry of neptunium, plutonium, americium, and curium looked nothing like the chemistry of the transition metals above them in the table. They looked much more like the rare earth elements, the lanthanides, elements 57 through 71. Seaborg had a radical idea. What if these new elements weren't transition metals at all? What if they were a second group of rare earth-like elements, filling a second set of f orbitals, analogous to the lanthanides? What if the periodic table needed to be rearranged? A second row pulled out from the bottom of the main body and placed below the lanthanides. This was heresy. Seaborg's colleagues told him he'd be ruining his career if he published such a radical rearrangement. The table was a sacred cow. You didn't just move elements around, but Seaborg trusted his chemistry, and in 1944, he proposed what he called the actinide concept, the idea that elements 89 through 103 form a series analogous to the lanthanides, a second row of F-block elements, and he was right. His rearrangement instantly made sense of the chemistry of the transuranium elements and predicted the properties of elements that hadn't been made yet. It also had a practical consequence that mattered during the war. By correctly understanding where americium and curium sat on the table, Seaborg could predict how to separate and purify them, which accelerated the discovery process. After the war, Seaborg's group at Berkeley became an element factory. Using the university's increasingly powerful particle accelerators, first the cyclotron, then the linear accelerator, they created one new element after another: berkelium, atomic number 97, named after Berkeley; californium, 98, after the state; einsteinium, 99, and fermium, 100, both discovered in the fallout from the first hydrogen bomb test, Ivy Mike, in 1952. They were found in the debris of the explosion, created by the extreme neutron flux of a thermonuclear detonation; mendelevium, 101, named after Mendeleev himself; and nobelium, 102, named after Alfred Nobel. Seaborg was awarded the Nobel Prize in Chemistry in 1951 for his discoveries of the transuranium elements. He's the only person to have an element named after him while he was still alive: Seaborgium, element 106, named in 1997. He reportedly joked that he was the only person whose name was also on the periodic table, which gave a whole new meaning to checking your mail. Seaborg was also chairman of the Atomic Energy Commission under Presidents Kennedy, Johnson, and Nixon, making him one of the most politically influential scientists of the 20th century. And yet he was, by all accounts, remarkably down to earth. He continued to teach undergraduate classes at Berkeley even when he was running a federal agency, and he was known for his dry humor, his love of hiking, and his genuine delight in mentoring young scientists. When he won the Nobel Prize, his mother reportedly said, "That's nice, Glenn," which might be the most Midwestern response to a Nobel Prize in history. But the process of creating these super-heavy elements was getting harder and harder. Each new element required smashing heavier and heavier nuclei together at enormous energies, and each successive element was less stable, with shorter and shorter half-lives. Element 100, fermium, has a longest-lived isotope with a half-life of about 100 days. Element 101, mendelevium, about 52 days. As you climb the periodic table, the atoms become increasingly unstable, and the time you have to study them shrinks from days to hours to minutes to seconds to fractions of a second. Some of the heaviest elements ever created have existed for only milliseconds before decaying, which makes studying them extraordinarily challenging. You're trying to do chemistry on atoms that exist for the blink of an eye, and then vanish, leaving behind only their decay products, as evidence they were ever there. And this brings us to one of the most fascinating and contentious chapters in the story of the periodic table: the race to create super-heavy elements. A race that played out during the Cold War, pitting American laboratories against Soviet ones, with a German team eventually joining the competition, and all of them arguing bitterly about who had discovered what, and who got to name it. This is sometimes called the Transfermium Wars, and it's one of those episodes in science that shows you just how human, how messy, how political even pure research can be. Here's the basic situation. After element 101, creating new elements required slamming large nuclei together, using particle accelerators, and hoping that, in the violent collision, enough protons and neutrons would stick together to form a new, heavier nucleus, instead of just flying apart. The problem is that heavy nuclei really don't want to exist. The electromagnetic force between all those positively charged protons tries to blow the nucleus apart, and only the strong nuclear force, which acts over extremely short distances, holds it together. As you add more and more protons, the repulsive electromagnetic force grows faster than the attractive nuclear force, and at some point, the nucleus becomes so unstable that it fissions, splits apart, almost immediately after forming. 3 laboratories led the charge. The Lawrence Berkeley National Laboratory in California, Seaborg's old stomping ground; the Joint Institute for Nuclear Research in Dubna, about 100 kilometers north of Moscow, and the Gesellschaft für Schwerionenforschung, abbreviated GSI, in Darmstadt, Germany. Each lab had different techniques. Berkeley favored hot fusion, smashing lighter projectiles into heavy targets at high energies. Dubna, under the leadership of the physicist Georgy Flerov, also used hot fusion, but with different combinations of projectiles and targets. GSI, led by Peter Armbruster and Gottfried Munzenberg, pioneered cold fusion. And I should clarify, this is nuclear physics cold fusion, which has nothing to do with the discredited claims about room temperature fusion in the late 1980s. Cold fusion in this context means using projectile target combinations that produce nuclei with less excitation energy, which means they're less likely to immediately fission. It's a matter of the temperature of the collision, metaphorically speaking. Through the 1960s, 70s, and 80s, these three labs created elements 104 through 112, and the priority disputes were fierce. Both Berkeley and Dubna claimed credit for elements 104 and 105, and they proposed different names. Berkeley wanted to call element 104 Rutherfordium and element 105 Hahnium. Dubna wanted to call them Kirchhovium and Nielsbohrium. For years, the elements existed in a bizarre nomenclature limbo, where different countries used different names for the same elements. The argument got so heated that the International Union of Pure and Applied Chemistry, IUPAC, the organization responsible for standardizing chemical nomenclature, had to step in. In 1997, after decades of controversy, IUPAC issued a final ruling on the names of elements 104 through 109. Element 104 became Rutherfordium. 105 became Dubnium, a compromise, named after neither Dubna's nor Berkeley's proposed names, but after the city of Dubna itself. Element 106 was Seaborgium. 107 was Bohrium. 108 was Hassium, after the German state of Hesse, where Darmstadt is located. And 109 was Meitnerium, named after the Austrian-Swedish physicist Lise Meitner, who had played a crucial role in the discovery of nuclear fission. Meitner, by the way, is another figure who deserves far more recognition than she typically receives. She was overlooked for the Nobel Prize, in a way that many historians consider one of the great injustices in the history of the awards. But that's a story for another night. The race continued. Through the late 1990s and into the 2000s, GSI and Dubna continued pushing forward. GSI created elements 110, 111, and 112, Darmstadtium, Roentgenium, and Copernicium. Dubna, in collaboration with the Lawrence Livermore National Laboratory in California, a new American partner, created elements 113 through 118. Element 113 it was also claimed by a team at RIKEN, the Japanese National Research Laboratory, led by Kosuke Morita. Morita's team had spent over a decade trying to create element 113, using a different approach from Dubna, and they finally succeeded in producing and detecting 3 atoms, just 3 atoms, between 2004 and 2012. IUPAC eventually awarded the naming rights to the Japanese team, and they named it Nihonium, after Nihon, the Japanese word for Japan. It was the first element named after an East Asian country, and a point of enormous national pride. And then there's element 118, oganesson. This one is special for several reasons. First, it sits at the bottom right corner of the periodic table, in the noble gas column, directly below radon. If the periodic table's patterns hold, oganesson should be a noble gas. But theoretical calculations suggest that at such high atomic numbers, the electrons are moving so fast, a significant fraction of the speed of light, that relativistic effects become important. The electrons closest to the nucleus contract inward, which changes the screening of the nuclear charge, which affects the outer electrons, which changes the chemistry. Some calculations predict that oganesson might not behave like a noble gas at all. It might actually be a reactive, perhaps even solid, element. Nobody knows for sure, because oganesson has only ever been produced a handful of times, and its longest-lived isotope has a half-life of less than a millisecond. You can't do chemistry on something that exists for less than 1,000th of a second. The other reason oganesson is special is its name. It was named after Yuri Oganessian, the Armenian-born physicist who led the Dubna team that created it. Oganessian was still alive when the element was named in 2016, making him only the second person to have an element named after him while living, the first being Seaborg. In the world of chemistry, that's about as close to immortality as you can get. Now, here's a question that naturally arises when you look at the bottom of the periodic table and see these incredibly heavy, incredibly unstable elements that exist for milliseconds at most. Why bother? If oganesson vanishes in 1,000th of a second, what's the point of creating it? Why spend decades and billions of dollars smashing nuclei together to make atoms that can't even be held or studied in any conventional sense? There are several answers, and they're all good ones. The first is the most straightforward, because the periodic table is a map, and we want to know what the map looks like. Does it end? Is there a final element? A heaviest possible atom? Or can we keep going? Nobody knows, and that's a genuine scientific question worth answering. The second answer is more specific and more exciting. It involves a theoretical prediction that has tantalized nuclear physicists for over 50 years. The idea of the island of stability. Here's the concept. As you add protons and neutrons to a nucleus, stability generally decreases. The heaviest elements are wildly unstable. But nuclear physicists have predicted that there might be certain combinations of protons and neutrons, certain magic numbers, as they're actually called, where the nuclear forces are particularly well balanced, creating pockets of relative stability in the sea of instability, an island of stability in an ocean of nuclear chaos. The most commonly predicted island centers around element 114, flerovium, or possibly elements 120 or 126. The idea is that an element at one of these magic numbers might have isotopes with half-lives of minutes, hours, days, maybe even years, long enough to actually study their chemistry, maybe even to see and touch them. If such an island exists, it would mean that there are super-heavy elements that could actually persist, that aren't just fleeting ghosts in a detector. Some theoretical models even predict half-lives of millions of years for certain super-heavy isotopes, though that's on the optimistic end. There's some tantalizing evidence. Flerovium, element 114, and its neighbor livermorium, element 116, do seem to be slightly more stable than their neighbors, which is consistent with the predictions. But we haven't reached the center of the island yet. Getting there requires creating isotopes with significantly more neutrons than we've been able to produce so far, and that's an enormous technical challenge. New accelerator facilities, like the Super Heavy Element Factory that opened at Dubna in 2019, are designed specifically to push toward these goals. And the third answer to why bother is perhaps the deepest one. These experiments test our understanding of nuclear physics at its extremes. They push the boundaries of quantum mechanics, of our models of the nuclear force, of relativistic effects in atoms. When we predict that oganesson might not behave like a noble gas because of relativistic electron effects, we're making predictions about how quantum mechanics and special relativity interact in extreme conditions. Making the element and testing those predictions, even for a millisecond, is a way of probing the fundamental laws of physics. Which brings us, finally, to where we are right now, to the periodic table as it exists today, in your lifetime, and to what it means for the world you live in every day. Because the periodic table isn't just an academic curiosity, it's the practical foundation of the material world. Every substance you encounter, every technology you use, every material that makes modern life possible, it all comes back to the elements and their properties. And those properties are written right there in the table, encoded in the position of each element, waiting to be read by anyone who knows how. Let's just take a walk through some of the elements that shape your daily life, because it's worth seeing how this abstract chart on the classroom wall connects to the phone in your pocket, the food on your plate, and the medicine in your cabinet. Start with carbon, element 6. Carbon is the backbone of all known life. Every protein, every strand of DNA, every molecule of fat and sugar and vitamin in your body is built on a framework of carbon atoms. The reason is carbon's extraordinary versatility. With 4 valence electrons, carbon can form stable bonds with up to 4 other atoms simultaneously, and it can bond to itself in chains, rings, branching networks, and 3-dimensional structures of enormous complexity. No other element comes close to this level of structural flexibility. Silicon, element 14, which is directly below carbon in the periodic table, has some of the same bonding properties, and science fiction writers have speculated about silicon-based life. But silicon-silicon bonds are weaker than carbon-carbon bonds, and silicon doesn't form the long, stable chains that carbon does. Life, as far as we know, needs carbon. The periodic table tells you why. It's right there in carbon's position, in its electron configuration, in its ability to form 4 covalent bonds. Now think about silicon in a completely different context. Silicon isn't the backbone of life, but it is the backbone of modern technology. The semiconductor industry, the one that makes the chips in your phone, your computer, your car, your television, your refrigerator, your watch, is built almost entirely on silicon. Why silicon? Because silicon is a semiconductor, meaning its electrical conductivity is between that of a conductor like copper and an insulator like glass. And crucially, you can precisely control silicon's conductivity by adding tiny amounts of other elements, a process called doping. Add a bit of phosphorus, element 15, which has 5 valence electrons instead of silicon's 4, and you get N-type silicon with excess negative charge carriers. Add a bit of boron, element 5, which has only 3 valence electrons, and you get P-type silicon with excess positive charge carriers. Put N-type and P-type silicon together, and you get a diode, a device that lets current flow in only one direction. Stack them differently, and you get a transistor. Put billions of transistors on a chip of silicon the size of your fingernail, and you get a modern processor. All of that, the entire digital revolution, comes from understanding the semiconductor properties of silicon, which come from its position in the periodic table, which comes from its electron configuration, which comes from quantum mechanics. The chain of causation runs all the way from Schrödinger's equation to the phone in your pocket. Or think about iron, element 26. Iron is the most widely used metal in the world, the backbone of modern infrastructure. Every bridge, every building, every car, every railway line relies on steel, which is primarily iron with a small percentage of carbon mixed in. The reason iron is so useful comes down to its unique combination of properties. It's strong, it's relatively abundant in Earth's crust, and the small addition of carbon transforms it from soft, easily deformed wrought iron into hard, resilient steel. The entire Industrial Revolution was powered by steel. And the reason there's so much iron in Earth's crust, and in the core of the Earth, and in the cores of all the rocky planets, takes us into astrophysics. Iron is the endpoint of stellar fusion. Inside a star, lighter elements are fused into heavier ones, releasing energy at each step: hydrogen into helium, helium into carbon, carbon into oxygen, and so on up the periodic table. But when you get to iron, the process stops. Fusing iron doesn't release energy, it consumes it. Iron is the ash of stellar burning, the bottom of the nuclear energy curve. It's the most stable nucleus in the universe, in a certain sense. And when a massive star runs out of fuel and its core is pure iron, fusion can no longer support it against gravity, and the star collapses and explodes in a supernova, scattering that iron, along with all the heavier elements created in the explosion, across space, where it eventually coalesces into planets and asteroids and, ultimately, into the hemoglobin molecules that carry oxygen through your blood right now. Think about that. The iron in your blood was forged in the core of a star that died before the sun was born. The periodic table connects you to the cosmos in the most literal way imaginable. Let me give you one more example, because it touches on something happening right now in geopolitics and technology. The rare earth elements. Despite their name, they're not actually all that rare in the Earth's crust. Some of them are more abundant than copper or lead. What makes them rare is that they're geologically dispersed, rarely concentrated in rich, easily mined deposits. The rare earths occupy a special place on the periodic table. They're the lanthanides, elements 57 through 71, that strip of elements that gets pulled out and placed below the main body of the table, and their chemistry, which arises from the filling of their 4f electron orbitals, gives them a distinctive set of properties that make them essential for modern technology. Neodymium, element 60, makes the world's strongest permanent magnets. Every electric vehicle motor, every wind turbine generator, every pair of earbuds you've ever worn uses neodymium magnets. Europium, element 63, and terbium, element 65, provide the red and green phosphors in display screens. Cerium, element 58, is used in catalytic converters that clean your car's exhaust. Erbium, element 68, is doped into the glass fibers of the Internet's backbone, amplifying light signals so they can travel thousands of miles without degrading. Without rare earth elements, you'd have no smartphones, no electric cars, no wind turbines, no fiber optic internet, no precision-guided military technology. The magnets alone are staggering. A single large wind turbine might contain 2 tons of rare earth magnets. A modern electric vehicle uses several kilograms. The world's demand for neodymium and its relatives has increased by an order of magnitude in the last 2 decades, and it's projected to keep rising sharply as the global transition to renewable energy accelerates. And because a large fraction of the world's rare earth processing is concentrated in a single country, China currently processes a dominant share of the global supply. The politics of the periodic table have become genuinely geopolitical. Trade disputes, export restrictions, and frantic efforts by other nations to develop alternative supply chains. All of this traces back to a handful of elements in the F block of the periodic table. Mendeleev didn't anticipate that his table would become a strategic document, but here we are, and there are stories like this for almost every element. Lithium, element 3, powers the rechargeable batteries in nearly every portable electronic device and electric vehicle. Platinum, element 78, catalyzes the chemical reactions in fuel cells and automotive converters. Titanium, element 22, provides the lightweight strength for aircraft frames and medical implants. Iodine, element 53, is essential for thyroid function. Iodine deficiency remains one of the world's most preventable causes of intellectual disability. Fluorine, element 9, hardens tooth enamel and makes non-stick coatings possible. Helium, element 2, cools the superconducting magnets in MRI machines. Gold, element 79, conducts electricity without corroding, and is used in the connectors of virtually every electronic circuit board. Every one of these applications traces back to the element's position on the periodic table, to its electron configuration, to its chemical and physical properties. The table isn't just a list. It's a key, a decoder ring for the material world. And that brings us to the frontier, to the questions that are still open, still being worked on, still keeping scientists up at night. Can we make element 119? Element 120? How far does the periodic table extend? Is there a limit? The theoretical models suggest that at some point, the nucleus becomes so large, so packed with protons all repelling each other, that no configuration of neutrons can hold it together. But exactly where that limit lies is unknown. Some models place it around element 170 or 172. Others suggest much lower. And the relativistic effects on electron configurations become so extreme at these high atomic numbers that the very concept of a period, the repeating pattern that gives the table its name, might break down. Element 120, if it's ever made, might not behave like the alkaline earth metals above it. Element 121 might start filling g orbitals, a type of electron orbital that's never been occupied in any known atom. The periodic table might need to be extended not just downward but outward, adding new blocks that don't exist in the current version. There are even questions about whether the periodic table itself, that beautiful rectangular grid, is the right shape for elements beyond 118. Maybe the table needs an additional block, a G block, to accommodate the new types of electron orbitals that would be filling in those super heavy elements. What would that look like? A wider table with an extra strip below the lanthanides and actinides? A three-dimensional table, spiraling outward? Chemists have been arguing about the optimal shape of the periodic table for decades, and the discovery of new elements might finally settle some of those arguments. Right now, laboratories in Russia, Japan, and elsewhere are actively trying to synthesize elements 119 and 120. The experiments are extraordinarily difficult. You're firing beams of trillions of atoms per second at a target, and if you're lucky, one collision in a billion will produce a single atom of the new element, which will exist for perhaps a millionth of a second before decaying. Detecting that single atom in the noise of all the other particles is like hearing a whisper in a hurricane. But the techniques keep improving. The accelerators keep getting more powerful, and the physicists and chemists keep pushing. And you know what's remarkable about all of this? The periodic table that Mendeleev sketched out in 1869, shuffling his little cards in St. Petersburg, arranging 63 elements by weight and chemical similarity. That table is fundamentally the same table we use today. We've filled in the gaps. We've added noble gases and actinides and super-heavy elements. We've understood why it works, electrons and shells and quantum mechanics. We've used it to build technologies that Mendeleev couldn't have imagined. But the underlying insight, the recognition that the elements follow a periodic pattern, that their properties repeat in a regular, predictable way, that insight was right. It was right in 1869, and it's right now, and it will still be right 1,000 years from now, because it reflects something real about the structure of matter, something deep about the way the universe is built. The periodic table is a portrait of nature, painted by generations of chemists, physicists, and engineers, each one adding a brushstroke, each one seeing a little further than the last. It started with Lavoisier's list of 33 elements, and grew through Dalton's atomic weights, Dobereiner's triads, Newland's octaves, Mendeleev's cards, Moseley's X-rays, the Curie's radioactivity, Seaborg's actinides, and the super-heavy element Hunter's particle accelerators. It spans from hydrogen, the simplest atom, one proton and one electron, created in the first minutes after the Big Bang, all the way to Oganesson, a fleeting arrangement of 118 protons and 176 neutrons that has only existed in a laboratory for fractions of a second. And every element on that table has a story. Every one of them was discovered by someone, often at great cost, sometimes at the cost of a life. Every one of them has a place in the world, a role it plays, a set of properties that makes it unique. And every one of them is, at bottom, just protons and neutrons and electrons, arranged in a particular pattern, following the rules of quantum mechanics, being exactly what the mathematics says they should be. So as you lie there tonight, breathing oxygen, element 8, exhaling carbon dioxide with its carbon, element 6, feeling the calcium in your bones and the iron in your blood, and the sodium and potassium firing signals through your nerves, and the phosphorus linking the nucleotides in your DNA. As you feel all of that, know that you are the periodic table, made flesh. You are 90-some elements, organized by 4 billion years of evolution, into something that can wonder about where those elements came from. That's extraordinary. That's worth thinking about as you drift off. The elements have been here since the stars forged them. They'll be here long after we're gone. But right now, in this particular arrangement, they're you, and they're doing something the stars never did. They're thinking about themselves. They're lying in the dark, half asleep, learning their own history. Mendeleev would have loved that. He spent his life trying to find the pattern in nature's building blocks, and one of those building blocks turned out to be the kind of thing that could find patterns. Carbon and hydrogen and oxygen and nitrogen and a few dozen other elements, arranged just so, and the universe starts asking questions about itself. Rest now. The elements will keep. The pattern will hold. And tomorrow, when you pick up your phone, silicon, lithium, aluminum, copper, rare earths, gold, or drink your water, hydrogen, oxygen, or step outside and breathe, nitrogen, oxygen, argon, you'll know, just a little better than you did before, what those things are, where they came from, and why they behave the way they do, because it's all in the table. It was always in the table, 70 boxes on a wall, and inside them, the whole universe. Sleep well. The atoms will keep their vigil without you. They always have. They always will. And when you wake, the table will be right where Mendeleev left it, waiting, patient, complete, and yet still growing. A map of everything there is, drawn by creatures made of the very stuff it maps. That's the periodic table. That's the whole beautiful, improbable story. Good night.